Settle in and let your breathing slow. The room is dim, the screens are soft, and somewhere outside, crickets do their night work. In front of you, a radio telescope waits, perfectly still, aimed at a sky that looks empty and isn't. You might think space is silent, but silence is just what happens when your ears are the wrong kind of instrument. Tonight, you listen the way the Sleepless Scientist listens, not for drama, but for tiny, ordinary patterns, the gentle static of Earth, and the slow handwriting of the cosmos. And tucked inside that quiet routine, we will find a single, impossibly brief pulse, the first fast radio burst, hiding in plain sight like a blink you almost missed. You are on the night shift, which is a polite way of saying you are watching a universe that mostly refuses to perform. The control room smells faintly like warm plastic and old coffee. Nothing is urgent. Nothing is cinematic. The loudest thing is the ventilation fan, doing its steady, annoyed whir, like it has been assigned to keep your thoughts from becoming too dramatic. In front of you, the radio telescope is not looking. Exactly, it is listening. And the strange part is that you already know how to do this. You have done it your whole life, with ears, with air, with pressure waves that wiggle your eardrums. A radio telescope just swaps out the eardrum for metal and swaps out air for vacuum, and then lets the sky tap on it with electromagnetic ripples you cannot see. Those ripples become signals. Signals become numbers. Numbers become a soft line on a screen. And you, unfortunately, become the person who stares at the line. It is almost soothing in the way that watching rain slide down a window can be soothing. You are not waiting for a monster. You are waiting for small changes, subtle bumps, a quiet rise and fall that might mean something. Most of the time, it means nothing. Most of the time, it means the universe is doing what it does best, continuing without checking whether you are impressed. The routine is simple. It is also endless. The telescope collects radio light, the receiver turns it into voltages, the computer packages it into data. The data scrolls and scrolls and scrolls, a slow river of information that is mostly just noise, like the hiss between stations on an old car radio. That is the comforting truth you learn early. Most nights are uneventful. The sky, for long stretches, is boring. And if you are trying to sleep, boring is a gift. But if you are trying to make a discovery, boring is also the baseline, the flat, calm sea that makes a single strange splash impossible to ignore. So you sit there in the dim glow of monitors. The dish outside stays aimed, obedient, and enormous, like a metal flower that only blooms at night. Somewhere far beyond it, stars are burning, planets are freezing, and galaxies are slowly rearranging themselves like tired furniture. None of that shows up on your screen as beauty. It shows up as a line. You learn to love the line anyway, because the line is honest. It does not care about your mood. It does not care about your theories. It only cares about what hit the dish and what your equipment accidentally added on the way. And while you are settling into that slow, patient listening, it helps to know what exactly a radio telescope is listening for. Radio waves are not little pellets. They are not particles you can scoop up. They are ripples in fields, traveling through space the way a swell travels across an ocean. Not a violent wave, not a crashing one. A long, gentle rise and fall that can pass through emptiness for millions or billions of years without getting tired. You cannot see them because your eyes are built for a narrow slice of the electromagnetic spectrum. Your eyes are picky. They like visible light. They like the kind of photons that bounce off walls and make colors. Radio waves are longer, slower in their wiggle, more stretched out. If visible light is a flickering, frantic strobe, radio is a calm, drawn-out breath. So, when you point a dish at the sky, you are not asking for sparkles. You are asking for faint, steady pressure on the receiver, a whisper that only becomes meaningful after you stare long enough. Different radio frequencies carry different kinds of stories. Some frequencies are crowded and loud, full of human chatter. Some are quieter, the way a side street is quieter than a highway. Astronomers talk about frequencies the way tired people talk about neighborhoods. This part of the dial is noisy. That part is calmer. Here you get interference. There you might hear something ancient. The sky itself has stations. A pulsar, for example, does not sing at every frequency equally. It ticks and flashes in a way that can be easier to catch in radio than in visible light. Clouds of cold hydrogen have their own favorite note, a particular radio frequency that becomes a kind of signature, a simple, steady stamp that says, yes, this is hydrogen, the most common element in the universe, still doing what it has always done. And then there is Earth. Earth is not a quiet place. Earth is a toddler with a drum set. Your phones leak radio signals. Your satellites broadcast. Your radar sweeps the sky. Even lightning, that quick white violence you can see from a distance, makes radio crackles you can detect from far away. There are microwave ovens and electric fences and car ignitions. There are network cables that hum if they are poorly shielded. There is a whole invisible fog of human technology, constantly talking over itself. So when you are listening for the faintest whispers of the cosmos, you have to do something very human. You have to go somewhere quiet. Not quiet like a library. Quiet like a high plateau. Quiet like the far edges of a country road, where there are no cell towers nearby and fewer devices leaking their private little electromagnetic tantrums into the air. Even then, you still have to build the dish big. Bigger dish means more collecting area, more sensitivity, more ability to catch a faint ripple and concentrate it onto a receiver. It is the same reason you cup your hand behind your ear when you cannot hear someone. You make a bigger surface to gather the sound. A radio dish is an enormous metal ear turned toward the cold. And in the control room, the results feel almost disappointingly ordinary. A radio telescope does not hand you a photograph. It hands you a stream of measurements. It hands you a plot. It hands you a file. It hands you an excuse to stay up late, staring at something that looks like it could be a stock market chart if the stock market were run by distant galaxies with no interest in profit. And yet, you keep listening, because once you understand how much static exists, you can appreciate why a single strange blip can feel like finding a lone footprint in fresh snow. The first thing you learn on nights like this is that the universe is not the only thing that can make a signal. The second thing you learn is that your equipment is not holy. A burst on the screen can come from a plane passing overhead. It can come from a satellite gliding through the telescope beam like a silent reflective bug. It can come from a malfunctioning cable that only misbehaves when the air is damp. It can come from an electrical relay clicking somewhere in the building, making a little sharp radio hiccup at exactly the wrong time. You start to develop a calm suspicion of everything. You see a sudden spike. Your heart does not leap. Not yet. You do not whisper, aliens. You whisper, us. Because it is almost always us. This is one of the gentler disciplines of science. It teaches you to treat excitement like a stray cat. You can look at it, you can acknowledge it, but you do not bring it inside the house until you are sure it will not destroy your furniture. So you check. You check the timestamps. You check other instruments. You check whether the same burst appears in another receiver. You check logs for known interference sources. You check whether the telescope was moving, whether it was tracking, whether it was pointed near the horizon where human noise is worst. You compare patterns night after night. You keep notes that are both obsessive and boring. At first, it feels like overkill. Later, it feels like the only way to stay sane. Because the universe, when it finally does something interesting, will not announce itself politely. It will look at first like junk. It will look like static. It will look like the same garbage you have been filtering out for weeks. And the only way you earn the right to notice the extraordinary is by becoming an expert in the ordinary. So you practice ruling out the boring explanations, one by one, not angrily, not impatiently, just steadily, like brushing sand off a stone, until the shape underneath begins to show. And then, after enough boring nights and careful checking, you finally reach the kind of moment that wakes up a whole field. The first fast radio burst did not arrive with trumpets. It did not arrive with a live broadcast and dramatic lighting. It arrived the way many discoveries arrive, as a ghost inside old data. You have to imagine stacks of recordings, long observations taken for one purpose, stored away, and then revisited later by someone with fresh eyes and a slightly different question. Science has this habit of leaving messages for itself. A telescope listens in one decade, and another decade finally understands what it heard. So, you are not necessarily in the moment of detection. You are in the moment of recognition. You are looking back through recordings, the way you might scroll through old photos on a phone at 2 in the morning, except these photos are made of signal strength over time, spread across radio frequencies like a barcode. It is quiet work. It is patient work. It is the kind of work that makes your shoulders tighten without you noticing. And then you see it. A pulse. Bright, sharp, impossibly brief. It is like a camera flash in a room that has been dark for hours. One instant of too much, and then back to the usual nothing. It is the kind of thing you might miss if you blink, or if you sip your coffee at the wrong second, or if your attention drifts to a different window on the screen. Congratulations! You have found a needle in a haystack made of other needles. What makes it different is not only that it is strong, it is also that it is fast. The whole event lasts only a tiny fraction of a second. It is over almost before your brain has time to label it as real. But a telescope does not need your brain to react quickly. The data is there. The timestamp is there. The pulse left its mark, and it is marked in a very particular way. When radio waves travel through space, they do not always arrive together. The lower frequencies can be delayed compared to the higher frequencies, depending on what the signal passed through. Space is not a perfect vacuum everywhere. It has plasma, thin clouds of charged particles drifting between stars and galaxies. Those particles interact with radio waves, slowing some parts of the signal slightly more than others. So the pulse does not appear as a perfectly vertical line across frequencies. It smears like a slanted brushstroke. High frequency arrives first, low frequency arrives after, stretched out by the medium in between. This effect is called dispersion. That is the technical term. The human translation is the universe made the signal arrive out of order, and that out of order arrival tells you something. It tells you the signal traveled through a lot of plasma. It tells you it crossed a lot of space. It suggests distance, not a local glitch in your electronics, not a lightning strike in the next county, not a satellite drifting through. Distance. That is the part that lands softly but heavily in your mind, because a brief pulse that is still strong after traveling that far must have started out absurdly energetic. It must have been a shout loud enough to remain a whisper by the time it reached your dish. The first of these was found in data from a big radio telescope in Australia, the Parkes Observatory. The pulse was spotted in recorded observations and eventually described in a scientific paper in the mid-2000s. It became known by a practical name, the Lorimer burst, after one of the people who reported it. And in the beginning, it was just one. One burst is a curiosity. One burst is a weird artifact. One burst is a story you tell at conferences with cautious language and slightly raised eyebrows. Because the universe is full of one-time events that turn out to be misunderstandings. So you do what scientists always do when the universe offers a single strange gift. You doubt it. You ask if it could be human-made interference. You ask if it could be a known class of object behaving badly. You ask if it could be a statistical fluke, a coincidence of noise that happened to line up in a convincing way. You look at the shape of the dispersion. You check if it matches what real space would do. You ask whether the signal could have come from within the telescope system itself. You ask whether it appears in multiple beams of the receiver, which might suggest a local source rather than a distant point in the sky. And for a while, the field sits in that uncomfortable middle place, the place where you have a signal that looks cosmic, but you only have one. One is not a population. One is not a pattern. One is a lonely dot on a graph that makes you nervous. Still, the dot stays there. It does not go away. It does not dissolve under skepticism. It just waits quietly in the literature like a strange animal sighting written down by a credible witness with no second sighting to confirm it. Then comes the slow shift, the part that makes this story feel less like a random glitch and more like a new category of thing. More bursts appear, not all at once, not with a dramatic montage. They appear the way raindrops appear on a window. First one, then another, hours later, then you stop thinking of it as an accident and start thinking of it as weather. Different telescopes begin to catch similar flashes. Some are found in real time. Some are dug out of archives. Some are noticed because computers get better at combing through vast amounts of data without getting bored. Because humans get bored. A human can stare at plots for hours, but humans have limits. A computer does not have a limit in the same way. A computer will inspect every slice of data with the same blank patience it uses to render your phone screen. It will look for patterns you tell it to look for. It will flag candidates. It will hand you a short list and let you feel like a genius for noticing what the machine dragged into the light. And as the years pass, the lonely dot becomes a scatter of dots. Fast radio bursts, FRB, spoken like separate letters because abbreviations are what scientists do when they want something to sound manageable. As if giving a mystery a short name makes it less mysterious. But the reality is calm and unsettling in a very specific way. The universe is not quiet. It is just quiet most of the time, and then, occasionally, it snaps. And those snaps are so brief and so bright that they feel almost rude, like someone flicking the lights on and off in a dark room while you are trying to rest. The bursts have a range of strengths, a range of dispersion measures. Some look like they came from far away. Some look closer. They do not all behave identically, which is both annoying and useful. Annoying because it suggests complexity. Useful because it hints this might not be one single phenomenon. It might be a family of phenomena. Different engines producing similar flashes, and in the middle of all this, you get one of the most important emotional changes in science. It is not joy. It is not triumph. It is relief. Relief that you are not imagining it. Because once you accept that these bursts are real and repeating, the next gentle step is asking what kind of place could make a signal like that. You begin building suspects, the way you might build a list of possible culprits for a noise in your house at night. It could be the wind. It could be the pipes. It could be the neighbor's cat. It could be something you do not want to name. In astronomy, the suspects tend to be things that are already extreme, because the cosmos does not usually produce bright, brief events from calm, ordinary objects. It produces them from dense leftovers, strong magnetic fields, violent collapses, fast spins. One suspect is a neutron star. This is what you get when a massive star dies and leaves behind a core so dense that atoms collapse. The electrons and protons merge into neutrons. The result is a star with the mass of the sun packed into something the size of a city. A city-sized star. Congratulations! You have found an object that makes Earth feel like a polite suggestion. Neutron stars can spin. Some spin fast, hundreds of times each second. They have magnetic fields that can be staggeringly strong. In the right conditions, they behave like cosmic lighthouses, sweeping beams through space. And a special kind of neutron star, called a magnetar, has magnetic fields so intense that they can stress the crust of the star itself. Starquakes, magnetic reconnections, bursts of energy. In a magnetar, the environment is not calm. It is like weather on a world where the atmosphere is made of magnetism. It is easy, in a bedtime story kind of way, to imagine a magnetar producing brief storms of radio light, a crackle, a snap, a pulse. But then you remember, you are a scientist, and imagination is not evidence. So you look for clues. Some fast radio bursts repeat. That is a big deal, because many catastrophic events do not repeat. A supernova happens once. A merger happens once. If a burst repeats, it suggests the source survives. It suggests a persistent engine, not a single explosion. Repeating bursts become their own sub-story. They narrow the suspects. They also widen the mystery because repeating sources can behave differently from one another. Some repeat often, some repeat rarely, some produce bursts that show complex structure, like little subpulses within the pulse, as if the signal itself is textured. You also learn that some bursts are polarized. The radio waves have a preferred orientation, like light filtered through sunglasses. Polarization can tell you about magnetic fields in the environment where the signal traveled. And sometimes the polarization rotates, twisted by magnetized plasma. This is called Faraday rotation, a technical name that translates to the signal's orientation got turned as it passed through a magnetic fog. Large rotation suggests strong magnetic fields along the path. That again, whispers magnetar, or something else energetic and dense. Still, you stay calm about it. The universe can make the same symptom from different causes. A fever can come from many illnesses. A burst can come from many engines. So you hold your suspects loosely. A city-sized neutron star with magnetic tantrums. A young pulsar. Maybe a compact object near a black hole. Maybe a dense region in a galaxy where strange things happen more often. And there is always the joke suspect, the one everyone mentions with a careful smile, then politely sets aside. Aliens. It is not that it is impossible in principle. It is that it is a bad first explanation. You do not start with the most complicated story when simpler ones exist. You start with physics you already know can produce extreme signals. You start with objects that already have a reputation for being loud in radio. And you remind yourself, gently, that nature is fully capable of sounding artificial. Pulsars were once nicknamed little green men because their regular pulses seemed too perfect. Nature, it turns out, loves making things that resemble engineering because physics, under the right constraints, produces patterns. The bursts are real, the sources are still being understood, and the path from signal to explanation is slow. To narrow the possibilities, you need to know where the burst lives, and that means learning how astronomers find an address for something that lasts only a blink. So you try to give a sub-second flash a home address, using instruments that were built for patience, not surprises. You start with an uncomfortable fact. One dish, by itself, is a terrible surveyor. A single radio telescope can tell you a burst happened, and roughly when. It can often tell you the frequency, sweep, the dispersion, the rough strength. But direction is fuzzier than you want. That is because a dish does not see the sky like your eyes do. It sees with something called a beam, a patch of sensitivity. Inside that patch, everything is blended together into one measurement. If the beam is wide, your direction is a guess with soft edges. Congratulations, you have detected a cosmic shout and misplaced it immediately. In the early days, that was the problem with fast radio bursts. Parkes, the famous Australian dish, had a large beam on the sky. It could hear a burst clearly, then shrug at the exact origin. The burst could have come from anywhere inside that patch. And that patch is not small. Not by astronomical standards. It is like hearing a twig snap in a forest and saying, somewhere east. Useful, but not enough to find the person holding the twig. So you do what you always do in science when nature is evasive. you recruit more hardware. Sometimes you use multiple beams on the same telescope. Some receivers have many horns, like a cluster of ears. If a burst appears strongly in one beam but not the others, that helps. If it appears in several beams at once, that often means it is local. Local is the polite word for disappointing, because local signals do that. They light up everything. A nearby source can splash into side lobes, into multiple beams. A real distant point source tends to be more picky. It should land cleanly in the beam you are actually pointing with. But multi-beam hints still only narrow the circle. To get an address you can mail a letter to, you need sharper vision. And in radio astronomy, sharp vision comes from separation. You spread your telescopes apart and you make them cooperate. This is where you start hearing the phrase interferometry. It sounds like a medical procedure, and it kind of is. You take two or more antennas, separated by distance. You combine their signals with precise timing. The basic trick is simple in spirit and cruel in practice. A wave arrives at one antenna, then a fraction later at another. That time delay depends on the direction the wave came from. Measure the delays well enough, and you get direction. Do it with enough antennas, in enough places, and the sky sharpens. The cruel part is the timing. Radio astronomers become obsessed with clocks in a way that is unhealthy. You cannot localize a millisecond burst with a casual wristwatch. You need timing accurate to tiny fractions of a second. You need atomic clocks or clock signals disciplined by satellites. You need to know down to a whisper when each antenna heard the flash. Then you cross-correlate. Another technical phrase. Human translation, you line up the wiggles and see how they match. When it works, it feels like magic that hates you personally. You turn a vague detection into coordinates. Not perfect at first, but good enough to point other telescopes. You can say, look here, in this small region of sky, and once you can say, look here, you unlock a second world of astronomy. Because radio alone is only one sense. You want to see what is sitting there in optical light or X-rays. You want context, the way you want a face to go with a voice. This is why localization matters so much for fast radio bursts. A burst is a blink, and then it is gone. If you cannot locate it, you cannot connect it to a galaxy. If you cannot connect it to a galaxy, you cannot measure its distance. And distance is everything. Distance tells you how much energy the source needed. Distance tells you whether you should blame local space weather or deep cosmos. Distance tells you whether you are looking at a rare explosion or common physics. It is the difference between a firefly and a lighthouse. But to get distance, you need a host galaxy, or something like it. You need a faint smudge of stars behind the burst position. You take that smudge, you split its light into a spectrum. You look for redshift, the stretching of light by cosmic expansion. Redshift is a gentle word for a big idea. The universe expands, so distant galaxies look shifted to redder colors. Measure that shift, and you estimate how far away it is. Far enough, and the burst becomes terrifying in a quiet way. Because a millisecond pulse from another galaxy is not casual. It is an immense release of power compressed into almost nothing, like emptying an ocean through a straw. In the time it takes to blink, the first really satisfying localizations came later, with better tools. You can think of arrays like the Very Large Array in New Mexico. Many dishes spread out, working as one instrument. Or newer survey instruments built to catch bursts and place them quickly. One of the most famous repeating bursts, for example, was tracked down. Once it had a location, people stared at that patch of sky obsessively. They found a small galaxy far away, forming stars. They found persistent radio emission near the burst position. Persistent emission is interesting because it does not blink. It sits there, steady like a pilot light. It suggests a nebula or a remnant or an engine still running, something living next to the thing that screams. That repeating source became a kind of training ground. It taught astronomers what to look for and what questions to ask. Is the environment magnetized, dense, turbulent? Is there evidence of recent star formation, of young remnants? But you also learn, slowly, that not all bursts live the same life. Some repeat, some do not, or at least not yet. Some live in messy star-forming galaxies. Some appear in calmer places, older stellar neighborhoods. So localization does not solve the mystery so much as multiply it. It gives you settings for the story, not the villain's confession. You get galaxies, you get neighborhoods, you get environments. And each environment suggests different engines. There is also a quieter gift in localization, one that feels less dramatic. Once you can place bursts, you can use them as probes, because the burst did not just come from somewhere. It traveled through everything between there and here. That travel leaves fingerprints. Remember dispersion, the arrival out of order. The amount of dispersion depends on free electrons along the path. Electrons in the source's neighborhood, in its host galaxy, electrons in intergalactic space, the thin plasma between galaxies. So, a fast radio burst becomes a flashlight shining through fog. You do not see the fog directly, but you see what it does to the beam. You measure dispersion and you infer electron content. You learn about the invisible matter between galaxies. In a universe obsessed with dark things, this is valuable. Astronomers have long suspected there are missing baryons. Baryons are ordinary matter, protons and neutrons, the familiar stuff. Not dark matter, just normal matter that is hard to see. Models say it should exist, but observations do not always find it. A lot of it is thought to be in warm, hot intergalactic medium, a thin, hot gas spread out between galaxies. Hard to image because it is faint and diffuse. But a fast radio burst does not care about imaging. It careens through that medium and gets delayed. The dispersion measure is a kind of accounting receipt. It tells you, roughly, how many electrons were in the way. So each burst is not only a mystery signal, it is also a survey of the space it crossed, a tiny data packet carrying information about the cosmic web. This is the part you might not expect. Late at night, you think the story is about a strange source, but the universe always upsells you. It turns the burst into a tool for cosmology. And then, in the most human twist, you realize the tool is inconvenient, because to use a burst as a probe, you need distance. To get distance, you need localization and host identification, and that means catching the burst, then catching it again with precision. A blink becomes a logistical project. You wait for real-time detection pipelines, software that listens continuously, flags a burst, sends an alert. Other telescopes swing over, like tired sentries responding to a bell. Optical telescopes look for a galaxy, for afterglow, for anything. Most of the time, they see nothing dramatic. That is fine. It is almost comforting. It suggests these bursts are not always paired with fireworks. Sometimes, nature just emits a pulse and moves on. No visible explosion, no shining aftermath, just a millisecond of radio, and then the ordinary sky. And so, slowly, you build a catalog. Positions, dispersion measures, pulse widths, polarizations, hosts when you can get them, limits when you cannot. A taxonomy grows, cautious and boring. Boring and therefore trustworthy. Because this is what science looks like from the inside. Not a single epiphany, but a slow tightening of constraints. Not one answer, but a narrowing of the space where answers can hide. You build a fence around the unknown. Then you make the fence smaller. And while you do all that, the night shift continues. The fans hum, the screens glow, the logs fill. Somewhere out in the sky, another burst may already be traveling. It might be halfway here, indifferent to your schedule. Speaking of schedules, fast radio bursts do not respect them. They do not arrive when your telescope is pointed at the right place. They do not ask permission before hitting your receiver. They are, in that way, very much like real life. So you adapt. You build instruments that watch huge chunks of sky at once. You accept lower sensitivity in exchange for sheer coverage. You let computers sift through the torrent in real time. You trade romance for efficiency. In Canada, for example, there is an instrument called CHIME. It does not look like a classic dish at all. It looks like long metal troughs staring upward. It watches a wide strip of sky, letting Earth's rotation do the scanning. It is less like a camera on a tripod, more like a security system that never blinks. These wide-field instruments turned fast radio bursts into routine, not emotionally routine, maybe, but statistically routine. They started finding bursts by the dozens, then the hundreds, and once you have hundreds, you can do population studies. Population studies are where mystery becomes manageable. You ask how common bursts are across the sky. You estimate how often they happen in the observable universe. You compare repeating versus apparently one-off sources. You look for clustering, for patterns in dispersion and brightness. And the universe answers, as it often does, with a shrug and more questions. Because some repeaters repeat in bursts of activity. They have active windows, days or weeks of chatter. Then they go quiet for months, like a radio friend ghosting you. Others repeat more steadily, or at least less predictably. Some bursts show scattering, smeared by turbulent plasma. Some are clean and sharp, like they traveled through emptier paths. Some show extreme Faraday rotation, suggesting dense magnetized environments. Others do not, suggesting calmer neighborhoods. So the field starts to suspect what you probably already felt. Fast radio burst is not one thing. It is a label for a symptom. A brief radio flash, seen from afar. Different engines can produce similar symptoms. That is not disappointing, even if it sounds like it. It is normal. It is how astrophysics works. Gamma ray bursts have multiple classes. Supernovae have types. Nature likes reusing outcomes. Speaking of engines, you return to your list of suspects, and now you get to revise it based on what localization taught you. Magnetars stay near the top. A magnetar is a neutron star with a magnetic field so strong it is obscene. Field lines twist and stress like a tight rubber band under strain. When they rearrange, they can release enormous energy, sometimes as X-rays, sometimes as gamma rays, sometimes as radio. In our own galaxy, we have magnetars. They occasionally produce giant flares. They are rare, but not mythical. And in the year 2020, something happened that felt like a clue. A magnetar in the Milky Way produced a bright radio burst. It was not identical to the extragalactic fast radio bursts, but it was uncomfortably similar in the right ways. It was like finding a small animal that resembles the monster's footprint. Not proof, but a strong suggestion that physics can do this nearby. So magnetars became more than a nice story. They became a working hypothesis with teeth. But again, teeth do not mean the whole animal, because some fast radio bursts seem to come from older galaxies, places where massive stars are less common, where new magnetars are fewer, unless you can make magnetars in other ways. For example, through mergers of white dwarfs or other delayed channels. Astronomers love delayed channels. A white dwarf is the leftover core of a sun-like star. It is dense, but not as dense as a neutron star. If two white dwarfs merge, strange outcomes follow. Sometimes a supernova, sometimes a more exotic remnant. Some models suggest you could end up with a neutron star, a magnetar born late. In an old galaxy, a youthful monster in a retirement home. It is not impossible. It is just complicated. And complicated is not wrong. It is just harder to test. There are other suspect engines as well. Some ideas involve neutron stars in binary systems. A neutron star interacting with a companion's wind. A magnetosphere disturbed periodically, producing bursts. This could explain some repeating patterns. Other ideas invoke black holes because of course they do. A black hole with an accretion disk, with jets, with magnetic fields, plasma falling in, magnetic lines snapping, energy spiking. But black hole models have to work hard to make millisecond structure. Millisecond structure is a tyrant. A thing that changes in a millisecond must be small. Not small by your standards, but small by cosmic standards. Light travels about 300 kilometers in a millisecond, so the region responsible cannot be vastly larger than that. That points back to compact objects, neutron stars, magnetospheres, tight zones near event horizons, not big fluffy nebulae, not entire galaxies acting as one. The size constraint is one of the simple, powerful ideas here. You cannot have a slow, spread-out source producing a sharp blink. The timing itself is a ruler. And then there is the question of brightness temperature, a technical term that translates to how intense is this emission? Some bursts are so intense that ordinary thermal emission cannot explain them. They must be coherent emission. Coherent means the waves act together, in phase, like a laser, but in radio, like a crowd chanting in sync instead of random chatter. Pulsars are famous for coherent radio emission. So again, pulsar-like physics, magnetar-like physics rises. But even if you settle emotionally on magnetars, you still have details. How exactly does the radio get made? How does it escape the surrounding plasma without being absorbed? Why do some repeat and others do not? You are forced to accept a soft truth. You can know the class of culprit without knowing the exact weapon. Science often works that way for a while. And all this careful narrowing depends on not fooling yourself. Which brings you back to the annoyance of false signals. Because fast radio bursts are dramatic, but the world is messy. You can waste years chasing something that was a microwave oven. This is not a metaphor, unfortunately. There was a time when a certain kind of burst was detected at parks. Short, sharp signals that looked suspiciously like cosmic bursts. They even had dispersion, like they traveled through plasma. People worried, then got excited, then worried again. These became known as peritons, named after a mythical creature, which was appropriate. They appeared in multiple beams, suggesting local origin. They occurred during office hours, which is always suspicious. Eventually, with careful detective work, the culprit emerged. A microwave oven on site opened before finishing its cycle. That door opening released a burst of radio interference. It mimicked an astrophysical event. Congratulations, you have discovered lunch. The periton story is not embarrassing, really. It is instructive. It reminds you how easy it is to be fooled by your own environment. It also reminds you how good scientists are at self-correction. They did not just declare victory. They dug in, they logged times, they looked for correlations, they found patterns, like the midday timing. They set traps, they monitored, they tested, and eventually, they caught the microwave. This is part of why the first fast radio burst was treated cautiously. Not because scientists hate wonder, because they have been lied to by vending machines and faulty cables. So even now, when you hear about an exciting new burst, there is a ritual. Is it seen at multiple observatories? Does it have the right dispersion sweep? Does it appear in one beam, consistent with a point source? Does it match known interference signatures? Only after that do you let your mind wander to distant galaxies. Only after that do you allow yourself the luxury of awe. A is earned in this job by surviving boredom. And boredom, tonight, is still your companion, because the act of localization, the act of narrowing, is slow. It is not the burst itself, which is fast. It is the follow-up, the analysis, the cross-checks, the hours of data, the calibration, the careful plotting. Calibration is one of those words that sounds tidy. It is not tidy. You have to account for how the instrument responds to signals. You have to correct for the atmosphere, for the electronics. You have to remove radio frequency interference, often called RFI. You cut out chunks of contaminated data like bruises in fruit. You learn that nature does not send signals directly into your brain. It sends them into a machine you built from imperfect parts. Then you try to unbuild the machine's fingerprints from the result. There is a strange intimacy in that. You know your instrument's quirks the way you know your own habits. You know which cable connector is temperamental. You know which frequency band gets hammered by satellites at dawn. And once you have a localization, a host, a distance, you begin to use it, not only to explain the burst, but to map the universe. The dispersion measure, combined with distance, lets you estimate matter. You can begin to weigh the intergalactic medium. You can compare burst properties across redshift. You can test whether bursts evolve over cosmic time. It is subtle work, almost gentle. It is also the kind of work that turns an anomaly into infrastructure. Fast radio bursts stop being just a weird phenomenon. They become a tool, like supernovae became distance markers, like pulsars became precision clocks. And while all that is happening, radio astronomy keeps doing its older jobs, because the dish does not only listen for new mysteries, it listens for the steady, the reliable, the repeating. Which means, as you sit in this dim control room, you are not alone. Your burst story shares space with other signals, other patterns that are less dramatic but more familiar. You have pulsars ticking away like exhausted metronomes. You have neutral hydrogen murmuring its simple line. You have planets crackling with magnetic storms. You have the background hiss of the early universe. The radio sky is not a single narrative. It is an overlapping choir, most of it quiet. And once you have learned to localize a blink, you start appreciating the long tones, the things that do not vanish in a millisecond, the things you can return to night after night and see again. Pulsars are a good place to drift next because they are the opposite of bursts. A fast radio burst is a surprise. A pulsar is a schedule, sometimes more reliable than your calendar. You imagine yourself not as the scientist now, but as the signal. You are radio light leaving a neutron star's magnetic pole. You are poured out in a narrow beam, like a flashlight in fog. As the star spins, your beam sweeps across space. Most of the time, you miss Earth completely. Space is large, Earth is small, and your beam is narrow. But when the geometry lines up, you pass over a dish. You tap the metal ear once per rotation. Tick, tick, tick. And those ticks can be astonishingly regular. Regular enough that astronomers use pulsars as clocks. Not perfect clocks, because pulsars glitch and wander, but still clocks that live in the galaxy. This regularity is why pulsars were once mistaken for engineering. A repeating pulse, precise, steady, indifferent. It looked like a beacon, like someone trying to say hello. Then it turned out to be a dead star spinning. Nature has no obligation to be poetic, but it often is anyway. Pulsars taught astronomers about neutron stars, about extreme density. They taught us that a star can die and keep speaking, not in light you can see, but in radio you can detect. And they taught us something else, how to handle timing. Because to detect a pulsar, you often fold data over many periods. You stack pulse after pulse to pull it out of noise. You take something faint and make it clear by repetition. Fast radio bursts refuse that method because they do not repeat predictably. They are single syllables, not steady words. But the techniques developed for pulsars still help. They trained astronomers to think in time series, in dispersion, in interference. So in a way, pulsars prepared the field for fast radio bursts. They taught everyone the dialect of the radio sky. They taught you what real astrophysical pulses look like. They taught you how messy the path can be between source and receiver. And speaking of messy paths, there is the simplest radio signal of all, the one that is not a pulse, not a burst, but a line. Neutral hydrogen, a proton, and an electron, the universe's basic furniture. When the electron flips its spin relative to the proton, it emits a photon, a radio photon, with a wavelength of about 21 centimeters. A quiet, specific note. No one hears it as a sound, of course. You translate it into a plot, a peak at the right frequency. And because the universe is expanding, that frequency gets shifted so you can map hydrogen across distances by its shifted note. This is how radio astronomers map galaxies in the dark, not by seeing stars, but by tracing gas. Gas is what galaxies eat, what they turn into stars. Gas is the future of light, still unlit. With hydrogen mapping, you can see spiral structure, you can see rotation curves, the way galaxies spin. Those rotation curves helped reveal dark matter because stars moved too fast. Gravity did not add up unless unseen mass was there. So, while fast radio bursts are exciting, hydrogen is foundational. It is slow science, steady science. It builds the scaffolding that later mysteries hang on. And then, closer to home, you have planets that talk in radio. Jupiter, for example, crackles with emissions tied to its magnetic field. Its magnetosphere is huge, a bubble bigger than the sun in some directions. Particles spiral along magnetic lines, generating radio noise, sometimes influenced by its moon Io, which drags material into the system. If you could listen with ears tuned to those frequencies, Jupiter would be loud. Not loud in a pleasant way, more like an electrical storm behind a wall. This is a comforting reminder, in an odd way. Radio astronomy is not only about distant galaxies, it is also about the physics of plasmas and magnetic fields nearby. The same principles repeat at different scales. And finally, there is the hum beneath everything. The cosmic microwave background is not radio in the strictest sense you imagine. It sits at microwave frequencies, higher than many radio bands, but it is part of the same electromagnetic family. It is the leftover glow from the early universe, cooled and stretched by expansion. It is a nearly uniform bath of photons, coming from every direction. Not because the universe is centered on you, because you are inside the afterglow, like a person inside fog. This background is a reminder that space is not empty. It is filled with ancient light, old enough to be almost numb. It is the universe's earliest photograph, blurred but still readable. Radio astronomers and microwave astronomers turn that hum into maps. They find tiny temperature variations, seeds of later structure. Those seeds grew into galaxies, clusters, the large-scale web. Your existence, in a very indirect sense, is written into that noise, and that brings you back to the feeling of the control room. The dish listening, the screen showing lines. Most of what you see is not fireworks, but small deviations, tiny bumps, little peaks, faint sweeps. This is why patience is not just a virtue here. It is the entire method, because when a burst does arrive, you have to treat it like a suspect. You check interference, you check beams, you check dispersion, you check whether the event matches known patterns of local noise. You do all the unromantic work first, And then, if it survives that, you allow it to be cosmic. This is also how scientists stay calm inside big mysteries, not by being emotionless, but by being structured. You build routines that keep you from falling in love with a hypothesis. You let skepticism do the boring part of the romance. In the day-to-day life of a radio astronomer, that looks like tea and logs. It looks like quiet conversations at odd hours. It looks like someone muttering about calibration tables. It looks like someone else celebrating a clean data set. Clean data is a rare luxury. You sit with collaborators who live in other time zones. Your emails arrive while you sleep, their questions waiting in the inbox. You answer, you revise, you run another pipeline. Science becomes a slow relay race across the globe. And when a result seems exciting, the first response is not applause, it is suspicion. Could it be RFI? Could it be an instrumental artifact? Could it be a selection effect in the search pipeline? Could your code be fooling you? Code is a quiet liar if you let it be. So you test it on known signals. You inject fake bursts into data and see if you recover them. You run the pipeline on empty sky to estimate false positives. You compare with independent pipelines written by other people. Independent confirmation is the lullaby of science. It is not soothing because it is pretty. It is soothing because it lowers the chance you are wrong. And when you finally publish, it is not the end. Publishing is a flag in the ground that says, here is what we think today. Tomorrow, someone else will bring new data. They will refine, correct, overturn, or deepen the story. That is not failure. That is the process. Fast radio bursts are still in that process. Some pieces have become clearer, like the existence of magnetar-like behavior. Some pieces remain blurred, like the full variety of sources. And the community holds that uncertainty with practiced calm, because you do not have to solve the universe in one night. You only have to keep watching it honestly, and somewhere in the middle of all this careful work, you notice a quieter human thing. The people doing it are not always heroic. They are often tired. They are sometimes cranky. They still have to file paperwork and maintain instruments and fix bugs. The romance of astronomy often leaves out the maintenance shift, but the maintenance shift is where discoveries survive. A poorly maintained receiver produces ghosts. A well-maintained system produces boring truth. So the culture around radio telescopes becomes a culture of caution. Not caution that avoids discovery, but caution that supports it. You celebrate a burst, but you also interrogate it. You let excitement in, but you do not let it drive. And that discipline makes the rare moments sweeter in a restrained way. When you localize a burst to a galaxy and others confirm it, when you see polarization indicating a strong magnetic environment, when a repeating source shows a pattern and the pattern persists, those are quiet victories. They do not feel like fireworks. They feel like a lock clicking open after hours of patience. A small mechanical sound. In the mind, speaking of locks clicking open, there is another kind of click. The click of realizing the radio sky has more surprises than you asked for. Because once fast radio bursts exist as a category, you start looking for cousins. Other transient radio events, other brief emissions, things that flare and fade, things that drift, things that pulse. The sky is full of transient phenomena. Some are known, some are new. Some come from stars, some from the sun, some from galaxies, and each one requires the same boring detective work. It is an ecosystem of signals, and you, sitting in that dim room, are part of the ecosystem too. Your attention is a resource, like collecting area. Your skepticism is a filter, like a band pass. Your tiredness is a noise source, like thermal hiss. So you build systems that compensate for your limits. Automated detection, machine learning classifiers, alert networks. You build a world where telescopes talk to each other faster than humans can. And still, the final step often comes back to a person. A person looking at a diagnostic plot, deciding if it is real. A person who has trained their eyes on years of boring lines. You do not need drama to do that. You need familiarity. That is why the story of fast radio bursts is also a story of craft. The craft of listening, filtering, localizing, and doubting. The craft of turning a millisecond flash into a scientific object. The craft of making the fleeting into the measurable. And as the nights accumulate, you find that radio astronomy has a certain rhythm. Long stretches of quiet, punctuated by small events. A lot like weather, except the storms are made of photons. A lot like life, except the scale is offensive. You can live comfortably inside that rhythm if you accept what it is, because the dish will keep listening whether you are awake or not. The data will keep flowing like a slow river, and every so often something will blink through, leaving a trace. A trace you can chase if you choose. For now, you stay with the chase, and you let it remain methodical. You have localized some bursts, but not all. You have host galaxies for a subset, but not a complete census. You have strong suspects, but not a single universal explanation. Which is fine. Mystery is not a crisis if you can measure it. And once you have measured it, you can start asking softer questions. How do bursts relate to their environments? How does burst rate change with galaxy type? What does dispersion tell you about the cosmic web? Questions that are big but answerable in pieces. So you keep collecting pieces, and while you do, other radio wonders keep humming in the background, steady and patient, waiting for their turn to be noticed in the noise. Sometimes that turn is something you did not build the telescope for at all. A slow drift in the baseline, a faint change in the background, a reminder that the radio sky is not just points and pulses. You notice it first as a kind of stubbornness in the data. You point the dish at an empty-looking patch, you integrate, you average, and the noise never quite goes to zero. It smooths, it settles, it becomes even, but it is still there, like a quiet hiss in a room you cannot fully seal. You might think the hiss is your equipment. Wrong, at least not entirely. Some of it is the receiver. Yes, warm electronics make their own gentle static. But some of it is the sky itself, a soft radio glow from our own galaxy, from distant galaxies, from the universe's leftover warmth. Space, inconveniently, is not blank. And once you start noticing that, you start noticing everything else that sits inside the quiet. Not flashes, not blinks, but regular, almost domestic sounds, the kinds of signals you can come back to again and again, like familiar late-night callers who never stop talking. One of those callers is the sun. You do not always think of the sun as a radio object because your eyes keep stealing the spotlight. But in radio, the sun is not a polite yellow circle. It is a restless ball of plasma, throwing tantrums in frequencies your skin cannot feel. When the sun gets active, it can flood a radio band with noise. It can flare, it can hiss, it can produce bursts of its own. Not the same as fast radio bursts, but still a reminder that plasma and magnetic fields love to radiate when they are stressed. And you know what the first response is every time. You check whether your cosmic excitement is actually solar weather dressed up as mystery. You keep an eye on space weather reports. You note the time of day. You remember that the Earth's ionosphere changes after sunset and changes again before dawn. It can refract radio waves, bend them slightly, distort them, add its own fingerprints. Even a quiet night has layers. Your job is to separate them. The ionosphere is one of those annoyances you can never fire. It is a thin shell of charged particles made by sunlight stripping electrons from atoms high in the atmosphere. It is the reason some radio stations bounce over the horizon at night when conditions are right. For astronomy, it is a moving lens you did not ask for. At low frequencies, the ionosphere can smear sources, wobble their apparent position, change polarization in subtle ways. It is not malicious. It is just there, being the sky's first filter between your dish and the rest of reality. So when you think about localizing a fast radio burst, you also think about calibration again, the ugly art of telling what the sky did versus what your planet did versus what your instrument did. And speaking of planets being unhelpful, Earth is not just an ionosphere. Earth is also an unlicensed broadcaster. There are parts of the radio spectrum reserved for astronomy, protected bands where transmitters are discouraged or forbidden. But the universe does not care about your paperwork, and neither do all humans. Sometimes signals leak into protected bands anyway. Sometimes satellites are too loud. Sometimes a distant radar sweeps right through your quiet neighborhood. And sometimes, even if everyone follows the rules, physics still betrays you. Reflections happen. Harmonics happen. Electronics create spurious signals at unexpected frequencies. A clean band becomes messy because the world is messy. So, radio astronomers develop habits that feel almost monastic. You take data. You flag interference. You throw away the contaminated parts without getting sentimental. You keep only what survived the gauntlet. In a way, your science is defined as much by what you discard as by what you keep. And that is why, when fast radio bursts became a real phenomenon, it forced a kind of new discipline on the whole field. You could no longer afford to treat the radio sky as something that changes slowly. You had to be ready for millisecond surprises hiding inside hours of calm. That changed the hardware. It changed the way people watch their own plots. You start building backends that can handle high time resolution, meaning they record the signal fast enough to resolve a millisecond event without smearing it into nothing. You store raw voltage data sometimes, not just averaged power, so you can do better processing later. Raw voltages are heavy. They take up storage. They are inconvenient. Congratulations, your discovery requires more hard drives, but the reward is that you can do more precise de-dispersion. De-dispersion is one of those words that sounds like a cleaning product. And it sort of is. You take the dispersed signal, the sweep across frequencies, and you mathematically reverse the delay, shifting each frequency channel by just the right amount so the pulse lines up in time. If you do it right, the pulse becomes sharp again. If you do it wrong, it smears out and disappears like a sentence stretched until it stops meaning anything. So you try many dispersion measures, many trial delays, hunting for the one that produces the sharpest pulse. It is like turning a focus ring on a camera, except you are focusing in time, not in space. This is where the routine can get hypnotic. You try a dispersion value. You check the result. You try another. You check again. Most of the time, nothing appears. Sometimes you get a candidate, and you zoom in, and it turns out to be interference. A little burst of local garbage that your algorithm found because it is hungry for patterns. And then, rarely, you get a pulse that sharpens as you de-disperse it. That sharpening is a kind of quiet confirmation. It means the sweep was real. It means the signal traveled through plasma the way astrophysical signals do. It is not perfect proof, but it is one of the fingerprints you trust. Trust is always conditional. And once you trust a burst enough to keep it, you start asking what else is inside it. Because a millisecond is short, but it is not featureless. Some bursts show substructure, multiple peaks packed into the same blink. Some show frequency drifting, where the brightest part slides downward in frequency as time passes, like a tiny falling whistle. You might think of it as a single flash, but sometimes it is more like a cluster of sparks, too close together for your intuition to separate. This is where you feel the limits of language. You call it a burst because you need a word, but the data can show complexity that makes the word feel like a lazy shortcut. And then there is scattering. Scattering is what happens when the radio wave passes through turbulent plasma, irregularities that act like a hall of mirrors. The pulse gets stretched and smeared, often with a characteristic tail. It is like hearing a clap in a room with echoes. The sharp start, then a fading wash. The presence of scattering tells you about the medium, about turbulence and density along the path. Sometimes it points to a messy environment near the source. Sometimes it points to our own galaxy's interstellar medium. Sometimes it is a mix, and that is the thing about radio signals. They are not just messages from a source, they are travelogues. They report on every place they have been, whether they wanted to or not. Which means, if you are patient, you can use them like medical imaging. You shine a burst through the cosmic web and infer what is inside, the way you use an X-ray to infer bone. This is why, as fast radio bursts became common, people started talking about them as cosmological probes, not just astrophysical curiosities. You can, in principle, use a large sample of bursts with known distances to map where the universe keeps its missing ordinary matter. You can compare dispersion measures with redshift. You can learn about the distribution of free electrons through cosmic time. You can also learn about magnetic fields through Faraday rotation. Rotation measure is the name, and it is measured in a way that feels like counting twists. The polarization angle rotates as a function of wavelength. Measure that relationship, and you infer the integrated magnetic field times electron density along the path. Integrated is the key word. It is the whole journey collapsed into one number. It is both powerful and frustrating, because you cannot always tell which segment of the path contributed what. Was the rotation mostly in the host galaxy? Was it near the source? Was it in a dense nebula? Or in the intergalactic medium? Sometimes you can tease it apart with models and comparisons. Sometimes you cannot. Sometimes the universe hands you a number and says, do your best. And you do your best, because that is the job. You take bursts with extreme rotation measures, and you suspect they live in highly magnetized environments, maybe near a massive black hole, or inside a young supernova remnant, or in a dense star-forming region with turbulent fields. You take bursts with modest rotation measures, and you suspect calmer paths. You look for correlations with galaxy type, with local star formation, with persistent radio sources. And because you are human, you also look for narratives. You want a tidy story. The universe does not. So you settle for families, a family of repeating bursts, some in active phases, some quiet. A family of non-repeating bursts, possibly from catastrophic events, or from engines that do not repeat often enough for you to catch them. You try to distinguish them statistically, but the categories resist, partly because you might be fooled by selection effects. Maybe many sources repeat, but you only see one burst because you stopped watching. Maybe some sources seem non-repeating because their repetition is rare or faint. The absence of evidence in astronomy is often evidence of your limited attention span. So you keep building better surveys, better coverage, better sensitivity, better time resolution, better algorithms, and you keep building networks. This is one of the quieter revolutions in modern astronomy, the way telescopes talk to each other. An instrument detects a transient. It sends an alert within seconds. Other observatories respond automatically. Robotic optical telescopes slew to the position. X-ray satellites check their fields. People coordinate across continents, not with shouting, mostly with messages and scripts and standardized formats. The drama is internal. On the outside, it is just a database entry, a circular, a set of coordinates. A blink becomes a collaboration. And while this is happening, you still do the bread and butter of radio astronomy, because the telescope schedule does not care about your personal obsessions. So, between bursts, you return to the steady wonders. You return to pulsars because they are not just clocks, they are laboratories. You can use pulsars to test general relativity because some pulsars sit in binary systems with other compact objects. As they orbit, their pulses arrive early and late in a predictable pattern. The timing variations encode the orbit, the masses, the effects of gravity. Pulsar timing is like having a lighthouse that also sends you its own GPS data, if you can decode it. In some systems, the orbit decays over time because energy is carried away by gravitational waves. This decay was measured in the famous Hulse-Taylor binary pulsar, long before detectors on Earth directly measured gravitational waves. It was indirect evidence, but strong evidence, that the universe really does let mass ripple space-time. You can fall asleep to that thought if you want. The idea that the galaxy contains clocks that slowly spiral inward, losing energy into the fabric of reality. Not romantic energy, accounting energy. And then there are millisecond pulsars, which are especially stable. Some are spun up by accreting material from a companion, a process called recycling. The pulsar steals angular momentum and becomes an insanely fast spinner, a neutron star turned into a precision metronome. These objects can be timed so accurately that they act like a galaxy-scale detector. If a gravitational wave passes between you and a pulsar, it slightly stretches and compresses space-time, shifting pulse arrival times. You cannot feel it directly, but with enough pulsars, timed over years, you can search for a correlated pattern, a background of gravitational waves from supermassive black hole binaries across the universe. A pulsar timing array is the name. The human translation is: you use dead stars as microphones for the universe's slowest vibrations. This is one of those ideas that sounds like science fiction, but is mostly spreadsheet work. You time pulses. You remove known effects, Earth's motion, clock errors, interstellar dispersion variations. You model noise. You do it again next week. You do it again next year. And eventually, if you are lucky and careful, you see a hint of a shared signal, a low-frequency gravitational wave. Background. This has started to appear in recent years, with multiple timing collaborations reporting evidence for it. Not a single loud event, but a statistical hum. A cosmic bass note, radio astronomy is good at hums, which brings you back to neutral hydrogen again, because hydrogen is not just a line, it is a map. The 21-centimeter line lets you trace gas in the Milky Way and in nearby galaxies. It lets you measure rotation curves and therefore infer dark matter distributions. It lets you see gas streams, tidal interactions, the messy ways galaxies exchange material. In optical images, galaxies look like crisp spirals and elegant ellipses. In hydrogen, they look like living things with trailing threads, with warped disks, with faint bridges connecting companions. The elegance is often just the bright part. The radio shows the rest. And then, if you go beyond individual galaxies, you can use hydrogen surveys to study large-scale structure, the cosmic web scaffolding. Some experiments aim to detect the collective 21-centimeter emission from huge numbers of distant galaxies, not individually resolved, but as a statistical field. This is called intensity mapping. It is like hearing a crowd rather than individual voices. From that crowd, you can infer the distribution of matter, the imprint of baryon acoustic oscillations, the gentle ripple pattern from the early universe that became a standard ruler in cosmology. It is strange how often astronomy comes back to rulers. A burst gives you a ruler in time. A hydrogen line gives you a ruler in frequency. The cosmic microwave background gives you a ruler in angular scale. Everything becomes measurement eventually, even wonder. And speaking of the cosmic microwave background, it is not just a uniform glow. It has tiny variations, small differences in temperature that correspond to density variations in the early universe. Those variations were measured by missions like COBE, then WMAP, then Planck. Each improved the resolution and sensitivity, turning a hazy map into a detailed portrait. From that portrait, you infer the age of the universe, the composition, the proportions of baryonic matter, and dark energy. You infer the geometry close to flat. You infer the initial conditions for structure formation. All of that comes from microwaves, the universe's baby picture stretched and cooled until it is gentle enough to bathe everything. The cosmic microwave background is an example of radio and microwave astronomy doing something almost opposite to fast radio bursts. Bursts are rare and brief. The background is everywhere and constant. One is a blink, the other is a stare, and your telescope, depending on how you use it, can do both. It can chase blinks, and it can measure stares. It can do transient surveys, and it can do deep integrations. It can listen to Jupiter crackle, and it can listen to a galaxy's hydrogen murmur. It can even listen to molecules, because radio astronomy is also chemistry. In cold interstellar clouds, molecules rotate and vibrate, emitting photons at characteristic radio and millimeter wavelengths. Carbon monoxide, ammonia, formaldehyde. The names sound like a cleaning aisle, but out there they are tracers of dense gas, of star-forming regions, of temperature and density. You point a radio telescope at a molecular cloud and you see lines, multiple peaks at different frequencies, each corresponding to a transition. From those lines, you infer velocity. Through Doppler shift, you infer turbulence. You infer infall and outflow, gas collapsing into protostars, jets carving cavities. Star formation is messy, and radio lets you see into the dust. Dust blocks optical light. Radio passes through more easily, so radio and millimeter telescopes become a kind of night vision for the galaxy's nurseries. The universe is always making stars, quietly behind curtains. And sometimes, in those nurseries, you get masers. A maser is like a laser, but in microwave frequencies. It is coherent amplification, often in regions around young stars or evolved stars. Masers can be extremely bright at specific frequencies, like neon signs in the radio spectrum. They can be used to measure distances through parallax because they are compact and bright, good reference points for very long baseline interferometry. Very long baseline interferometry is when you use antennas separated by continents, sometimes by the size of Earth, to get extremely fine angular resolution. You record data at each site with precise timing, then correlate it later. It is like building an Earth-sized telescope, except you cannot physically connect the dishes, so you connect them with clocks and math. This technique has produced some of the sharpest images in astronomy, including the famous images of black hole shadows, the ring-like glow around the event horizons of M87 star and Sagittarius A star. Those images are not direct photographs in the way your brain wants. They are reconstructions from interferometric data. They are what you get when you let an Earth-sized instrument stare at a source and combine signals with insane precision. And the fact that this works at all is one of those quiet miracles of human engineering, the kind you do not celebrate properly because you are too busy debugging. But it also ties back to fast radio bursts, because localization and characterization often relies on interferometric arrays. You want precise positions. You want to connect bursts to hosts. You want to see persistent radio sources nearby. You want resolution, and resolution is expensive. It costs money, yes, but it also costs time, attention, and a lot of carefully managed complexity. So you build pipelines that handle that complexity without making you cry. You write code that pulls data from multiple antennas, aligns it, calibrates it, images it, searches for transients. You run it, and it fails. You fix one bug and find two more. This is the part of science that is rarely shown in documentaries. because it is not visually appealing. But at night, in a control room, it is the reality. The universe is not the only source of noise. Your software is too. So the culture of radio astronomy becomes a culture of verification. You do not just process the data once. You process it in multiple ways. You test with simulations. You compare with known sources. You track system temperature. System temperature is another technical phrase that translates to how noisy is your instrument, in a way you can quantify. The sky has a temperature in radio because brightness corresponds to power. The receiver has a temperature because it adds noise. The atmosphere can add noise. Even the ground can leak into side lobes. You model all of it. Then you subtract as best you can. Subtraction is the act of turning the world into a cleaner world on paper. And after subtraction, you search for pulses, for lines, for slow variations, for anything that stands out against what you think you understand. It is an endless game of pattern recognition with consequences. And because you are human, you occasionally get fooled. Sometimes you get fooled by peritons, by microwaves, by human technology. Sometimes you get fooled by your own expectations. There is a classic trap in transient searches. If you tune your algorithms too aggressively, you find too many candidates. Most of them false. If you tune too conservatively, you miss real events. So you pick thresholds. You decide what signal-to-noise ratio counts as interesting. Signal-to-noise ratio is a simple concept. It is how tall a peak is compared to the background variation. But deciding the cutoff is not purely mathematical. It is practical. Too low, and you drown in junk. Too high, and you throw away wonders. So you compromise. And because compromise is uncomfortable, you rely on follow-up. If something is real, you want to see it again, or see it with another telescope, or see it in another band. But fast radio bursts do not always cooperate. Many are one-offs or appear to be. You cannot schedule them. You cannot demand a repeat, so you get creative. You build commensal searches, meaning you search for bursts while the telescope is doing something else. You piggyback on other observations, harvesting transients from data that was taken for other purposes. This is, in a way, how the first burst was found too hidden in data taken for pulsar studies. The universe likes to hide new phenomena inside old projects because the sky does not care what you intended. And as burst catalogs grow, you start doing a kind of quiet sociology of the sources. You look at burst rates. You fit distributions, power laws, and log normals, trying to see if the population has a characteristic energy scale or if it is scale-free. Scale-free is a fancy way of saying there is no typical size, just many small events and a few big ones. Earthquakes have that property. So do some astrophysical phenomena. If fast radio bursts have it too, it suggests something about the underlying engine, about how energy is released. Maybe it is avalanche-like, magnetic stress building, and then releasing in bursts of different sizes. Maybe you do not commit too hard. You just measure. You look at waiting times between bursts for repeaters. Do they follow a Poisson process, like random independent events? Or do they cluster like storms with lulls? Some repeaters show clustering active windows, which suggests the engine has states. A state could be a magnetosphere configuration. A state could be interaction with a companion. A state could be a precessing beam that sometimes points at Earth and sometimes does not. Precession is like a spinning top, wobbling, changing the direction of its axis. A neutron star could precess if its shape is slightly asymmetric. That could modulate burst visibility. It is another possible story. The list of possible stories is long. You shorten it by asking what is consistent with all observed facts. That is always the game. And along the way, you learn a lot about plasma astrophysics, the physics of charged particles and electromagnetic fields in extreme conditions. Plasma is the most common state of matter in the universe. Stars are plasma. The interstellar medium is partly plasma. The intergalactic medium is plasma. Even your own body contains plasma in a limited sense because your blood carries charged ions, though you would not want to treat yourself like a magnetar. The point is, plasma behaves differently from a neutral gas. It responds to magnetic fields. It can support waves and instabilities. It can accelerate particles to high energies. And coherent radio emission, like pulsars produce, likely involves plasma processes, bunching of charges, emission mechanisms that are still not fully understood in detail. Even pulsars, discovered in the 1960s, are not completely solved in every microphysical sense. So, it is not surprising that fast radio bursts, a newer phenomenon, remain partly mysterious. It is actually comforting in a strange way. It means the universe still has corners that do not yield immediately. It means you can still do basic discovery, not just precision measurement. But discovery, again, is mostly boring. It is building instruments, it is writing code. It is checking logs, it is being wrong, and then less wrong. Which brings you back to the people, because behind every burst catalog is a small army of tired specialists. Some are instrumentalists, people who understand the hardware intimately. Some are data analysts, people who understand the pipelines. Some are theorists, building models that try to generate the observed properties. And they all have different instincts. Instrumentalists see a weird pulse and think of cable reflections and filter responses. Analysts see it and think of selection bias and thresholding. Theorists see it and think of magnetospheres and shocks. Everyone is, in their own way, trying to subtract themselves from the result, trying to see what is actually there. And this is why conferences about fast radio bursts can have a particular energy. Even if the people are exhausted, you get a new localization. You get a new repeater with a strange period. You get a burst with extreme polarization. You get a possible association with a supernova remnant or with a star-forming region. And then the room does what it always does. It asks, is it real? How do you know? What are the systematics? What did you assume? The questions are not hostile. They are protective. Because being fooled hurts. Not emotionally usually, just professionally, and in wasted time. And as the field matures, the questions get better. They become less about whether fast radio bursts exist and more about how many kinds there are and what they can be used for. Because the moment you accept that bursts are common, you start thinking about applications. One application is probing the intergalactic medium, as you already know. Another is measuring the baryon content of galaxy halos. When a burst passes through a galaxy's circumgalactic medium, the diffuse gas surrounding galaxies, it contributes to dispersion and scattering. With enough bursts passing behind foreground galaxies, you can statistically detect that contribution. You can map invisible gas around galaxies. You can, in effect, weigh the halos. Another application is searching for gravitational lensing. If a burst passes near a massive object, its path can be bent, creating multiple images that arrive at slightly different times. For a millisecond burst, this could produce a repeating echo separated by milliseconds or seconds, depending on the lens mass. Detecting such lensing could probe compact dark matter candidates or study the mass distribution in galaxies. It is tricky because you need high time resolution and careful analysis, but the idea sits there, quietly tempting. Fast radio bursts are so short that they make excellent clocks for such tests. Any duplication stands out. And then there is the possibility of using bursts to study reionization, the epoch when the first stars and galaxies ionized the neutral hydrogen in the universe, making the intergalactic medium transparent to ultraviolet light. Dispersion depends on free electrons, which depend on ionization. In principle, bursts at very high redshift could probe the ionization history. In practice, finding bursts that far is hard. The universe is kind enough to produce bursts, but not kind enough to place them conveniently. So you keep building more sensitive surveys. You build arrays. You build dishes with phased array feeds, multiple beams on the sky at once. You build real-time triggering. You create an ecosystem of instruments. Some are good at finding many bursts, like wide-field instruments. Some are good at localizing precisely, like interferometers. Some are good at follow-up in other bands. You coordinate, and in that coordination, you start to see a new kind of routine emerge. A routine that is not a person staring at one screen, but a network of machines and people making decisions quickly. Still, the night shift feels similar, because even with automation, someone has to check. Someone has to decide whether to wake someone else up. There is always a human somewhere being pulled out of sleep by a millisecond. Congratulations! Your job is to be tired for science. And once you accept that, you start noticing the human rituals that keep the whole thing calm. There is the tea, of course. There is the quiet humor. There is the habit of naming things in ways that make them feel less terrifying. Burst, repeater, candidate, event. There is the habit of writing careful papers full of caveats. Caveats are the universe's pillow. They soften the impact of being wrong. And there is the slow joy of shared discovery, not the loud kind. The kind where you open a draft from a collaborator and see a plot that looks cleaner than yesterday. The kind where a residual disappears after you fix a calibration error. The kind where an independent team reports a similar result and you feel your shoulders drop. We are not imagining it. That is a powerful sentence in any science. And while fast radio bursts remain a frontier, radio astronomy as a whole has lived through many frontiers before. Each time, the pattern is similar. First, you see something weird, then you doubt it. Then you see it again. Then you build instruments around it. Then it becomes routine, and your sense of wonder migrates to the next weird thing. Pulsars were weird. Then they became tools. Quasars were weird. Then they became tools. The cosmic microwave background was a weird hiss. Then it became a cornerstone. Fast radio bursts are in that transition. They are still weird, but they are also becoming useful. And there is something almost comforting about usefulness. It means the mystery is being domesticated slowly into the everyday life of astronomy. Not solved, domesticated. You can live with it. And to live with it, you stay calm inside uncertainty. You do not demand a final answer tonight. You do not demand that every burst fit into a single explanation. You let the data accumulate. You let the catalog grow. You let the universe show you its habits, 1 millisecond at a time. It is slow because everything important is slow, even when it comes in blinks. Even a blink takes years to understand. And in the meantime, you keep returning to the control room, to the screens, to the soft glow of plots. You watch for the line to jump. You watch for the frequency sweep. You watch for the telltale shape of something that crossed interstellar and intergalactic space and still arrived as a coherent packet. And when you see something, you do what you always do first. You assume it is boring. You check the local interference monitors. You check the beam pattern. You check whether it hit multiple beams. You check whether the dispersion looks like a real plasma sweep or like a cheap imitation. You check whether it occurred when someone opened a microwave. You check whether it lines up with known satellites. You check whether the sun was active. Only after all that, you let yourself write the word astrophysical in your notes. Astrophysical is a long word for not our fault. And once you write it, you begin the next round of slow questions. Is it repeating? Can we localize it? Can we get a host? What is the rotation measure? What is the scattering? Does it have substructure? Does it drift in frequency? Each question is a small step, and each step is designed to be survivable on little sleep. This is how scientists stay calm, not by having fewer mysteries, but by having a method that lets them hold mysteries without panic. And the method is, in essence, patience made formal. A pipeline, a checklist, a culture of doubt, a willingness to be bored until boredom is interrupted. Because boredom is not the enemy here. Boredom is the baseline that makes the universe's rare messages visible. And somewhere out beyond the dish, beyond the ionosphere, beyond the satellites and the human noise, the radio sky keeps doing what it does, emitting, drifting, crackling, humming. Not for you, just because physics allows it. And you, sitting in the dim light, get to eavesdrop. You get to turn that indifferent activity into knowledge, slowly. And as your logs fill with bursts and pulses and lines, you start to notice the strange intimacy of it all. You will never touch a magnetar. You will never visit a distant galaxy. You will never feel the intergalactic medium on your skin, but you can still measure it. A millisecond pulse arrives, and it carries the signature of plasma that has been drifting between galaxies since before your species had language. It is absurd when you say it out loud. So you do not say it out loud. You just write down the dispersion measure and keep going, because in the end, the control room does not reward poetry. It rewards consistency. It rewards the quiet discipline of showing up again night after night to listen for things that do not care whether you are listening. And as the screens continue their soft watch, you find that the strangest comfort in radio astronomy is this. Even the most fleeting signal still has to obey the same rules as everything else. It must travel. It must disperse. It must scatter. It must arrive. And if it arrives, you can eventually make a place for it in your understanding. Not a final place, just a place. A labeled drawer in a cabinet that will never stop growing. So you keep listening, and you let the radio sky keep adding to the collection. Not just bursts, but all the other gentle wonders that share the spectrum, waiting for their turn to stand out against the noise. And the funny thing is, the more drawers you build, the more the cabinet starts looking like a home. You sit there, lit by monitor glow, and you realize the night shift has a shape. It is not heroic. It is repetitive. It is small decisions made correctly, over and over, while the sky refuses to clap. You learn to love the parts that never make the headlines. The calibration scans on a known source, the quiet check that your system temperature has not crept upward, the dull satisfaction of a clean bandpass flat where it should be flat, because this is how you stay calm inside big mysteries. You do not wrestle the unknown directly. You build a boring routine around it, like sandbags around a river, and you let the river do what it does. Even the first fast radio burst, the one dug out of old parks data, was only possible because someone did not throw the data away. Someone archived it. Someone labeled it. Someone kept it in a format that a later human could still open without swearing too loudly. That is an unglamorous kind of kindness. The kind science runs on. And when the bursts kept showing up, the field did what it always does. It built a social immune system. Not perfect, just functional. One group finds a candidate. Another group checks whether it matches known interference. A third group tries to localize it. Someone else writes the code again, independently, just to see if the result survives being handled by different hands. You do not get certainty from confidence. You get it from redundancy. The good news is that the universe cannot forge your cross-checks forever. The bad news is that humans can waste years forging them for the universe, by accident, with sloppy cables and optimistic software. So you develop rituals that look dull from the outside. But from the inside, they are the difference between a discovery and a microwave dinner. You keep a list of satellites that like to pass through your bands. You keep an interference database, a little bestiary of human noise. You learn the signature of aircraft radar, the way it sweeps and repeats. You recognize the thin line of a communication signal that bleeds into your protected frequencies like a neighbor's music through a wall. Then you see a burst again, and you feel the reflex. You do not celebrate. You investigate. Does it appear in one beam or many? Does dispersion make it sharper? Does the polarization behave like sky, not like hardware? Do other observatories see it in the same time window? And if you get enough yes answers, you do something that sounds simple and is not. You tell the rest of humanity politely that a millisecond flash crossed the universe and hit your dish. That sentence should feel like magic, but in practice, it feels like paperwork, a circular, a database entry, a plot in a draft, a meeting where someone asks again whether the timing calibration is correct. Someone always asks. They are not being cruel, they are being useful. You start to understand that modern astronomy is not one person and one telescope. It is an ecosystem that stays awake in shifts. A wide field instrument finds the flash. An interferometer pins it down. An optical telescope finds the host galaxy. A spectrograph measures the redshift. A theorist tries to make the numbers behave. And you The tired human in the middle become a kind of translator. You translate dish voltage into a burst profile. You translate dispersion measure into a rough electron count. You translate a faint galaxy smudge into a distance. You translate distance into an energy budget that makes your skin itch because nature is spending that much energy in the time it takes you to blink. Then you do the calming thing. You write it down and you move on to the next event because there is always a next event if you wait long enough. And waiting is the real skill here. Waiting without daydreaming too hard. Waiting without turning every spike into a story. Waiting with enough skepticism to keep yourself honest and enough curiosity to keep yourself awake. That balance is the whole profession. Out there, the radio sky keeps behaving like a city at night, mostly quiet from a distance, but never truly asleep. A few steady streetlights, your pulsars, ticking along. A distant highway hiss, your galactic background. A sudden siren, a fast radio burst, gone before you can look up. You do not need the city to be kind to understand it. You only need it to be consistent. And it is. Electrons still disperse signals. Turbulence still scatters them. Magnetic fields still twist polarization. Space still refuses to be empty. The same rules apply whether the source is a magnetar in your own galaxy or a repeater in a star-forming galaxy far away. That is the comfort hiding inside cosmic horror. The universe is indifferent, yes, but it is also lawful. It does not get to surprise you with new physics every time it wants attention. It has to work with what it has, so you let yourself imagine the burst's journey one last time, not as romance, but as logistics. A compact object flares, coherently, briefly. The radio wavefront expands, thinning, spreading. It threads the host galaxy's gas, picking up delay. It enters the intergalactic medium, the cosmic web's thin plasma, collecting more dispersion like dust on a coat. It passes through the Milky Way's own interstellar haze, gathering one more layer of delay and scattering. Then, it hits the ionosphere, the last annoying veil. Then, it hits your dish. Then, it becomes numbers. And you, sitting in the control room, decide whether the numbers deserve a new draw. If they do, you label it carefully. You do not label it with certainty you do not have. You give it coordinates, and a time, and a dispersion measure, and maybe a rotation measure if you are lucky. You give it a name that is mostly a date, because astronomers are not poets when they are being responsible. Somewhere, someone else will open that drawer later. They will compare it to a larger sample. They will test a better model. They will notice a pattern you missed because you were human and it was late. That is fine. That is the point. The night does not demand you solve everything. It only asks you to listen well enough that the next person has something honest to work with. And in that way, even the fast radio burst story becomes gentle. Not because the bursts are gentle, they are not, but because the process is steady. A blink arrives, you verify it, you localize it if you can, you add it to the catalog, you go back to waiting. Outside, the dish keeps its patient posture, aimed at blackness that is full of events you will never catch. Most of reality will pass without a witness, and it will not be diminished by that. But sometimes, a millisecond flash will make it all the way here, intact enough to measure. That is not a promise. It is a possibility. And as your screens continue to glow in the quiet, you can let that possibility sit at the edge of your mind, not as a problem to solve, but as a rhythm the universe keeps, even when you fall asleep. Somewhere beyond your roofline, beyond the ionosphere's thin shimmer, the next message